Awesome. Well, good evening, everybody. Thank you for your time. I am going to try not to bore you guys to death. I've got 20 minutes. I'll probably go pretty close to that, maybe a little bit over since we have a little more time. I figure I'll start by just introducing myself so you know who the heck is up there talking to you. I'm Jason Harmon. I'm a solutions architect for GRAID. I've been with GRAID for almost 6 months now. Before that, I was selling SSDs for some of the big SSD suppliers who actually work for two of the three biggest ones. And before that, I was at Intel. And before that, I was at Flextronics, where I was leading the hyperscale, rack scale integration division for them. So here, I am now pushing bits versus pushing racks. And as we all know, that data storage is kind of like plumbing. It's an unnecessary evil. It's something we all don't like to get excited about, but nothing happens without it. So let me give you a little intro for who GRAID is, because most of you probably haven't heard about us. We're still in the, we're a Series B startup. We're actually very well funded, and we have a lot of very smart people. We are doing traditional RAID, but we're doing it with a twist. Rather than use an SoC like some of our competitors, we're actually using a NVIDIA GPU to accelerate and do the parity calculations. Two things happens. GPUs are excellent at doing simple math very, very quickly in a parallel fashion, which is basically what RAID is. Second, we're not wiring through a card anymore like traditional RAID cards. We're now actually going across a PCI bus, parity is done on the GPU, so our solution is not in the way of that data flow. And I'm sorry, that jumped ahead. We've got a lot of accolades. We're actually based here in the Valley. Our R&D is in Taiwan. Our development's in Taiwan. We're actually expanding our development here in the Bay as well. Jensen actually gave us a shout out in his keynote at the NVIDIA convention earlier this year, and we've got a lot of awards behind us. So now the slide you've already seen, sorry about that. We know what's going on with data. It's huge. It's 90% of the world's data has been created in the past 2 years. That's incredible. And I think it's going to be doubling every 4 years. I think that number is low personally. All the executives, I'm not an executive, I'm worried about it too. How the heck are we going to use all these bigger growing data lakes and then feed these AI machines, these HPC machines, and actually get results that actually mean something out of it? And really, the end result is a lot of these GPUs are getting starved. They're just not getting enough data where they can do their magic and spit out meaningful results. And we know what these cards cost. $15,000, $25,000, and up and up and up. So the challenge around storage, the AI with storage with AI is, again, how do we feed the GPU? How do we keep that beast hungry and well satisfied? Free up CPU resources. When we talk about AI, traditionally we are talking about GPU-based solutions, but that's not all of them. There's still quite a few models, especially when it comes to data preparation, that's still very CPU heavy. And if you start to do your RAID on a CPU, software-based RAID, you're not able to use those resources. And especially when you start to get the larger data sets and larger, I use the word spindles, but more drives, you really start to choke that CPU pretty dramatically. And, you know, as these data sets get bigger and bigger and more complicated, more likely of bit rot happening somewhere along the line in one of these drives or along many of these drives is real. And what happens when that happens? Let's say you've got a multi-petabyte data set. You have to throw it away? Maybe. So, like I kind of hinted at, all those are kind of an ROI. How do you best utilize your hardware? How do you make sure your data is going to be integral and not going to lose any of it? Make sure you don't have to repeat it. Make sure you don't have to use your resources to recreate it. All this stuff. So you come down to performance, resilience, and both of those added together is your ROI. And I apologize if I knew this was going to be this small, I would have made bigger fonts, so it's my fault. Performance is easy. Feed the beast. How much get the IOPS, keep your latency as low as possible, make sure everything is just happening as it needs to happen. Result, you get your bottlenecks out of the way. Resilience, again, that data is only as good as how accurate it is. If you start to have errors in there, your entire data set may be crap. What do you have to do? Restore it, at least to the last checkpoint, maybe completely, maybe recreate it. A lot of AI learning models are still done with human intervention manually for part of the indexes and part of the making sure that data actually aligns with reality even today. And you put those all together, you're eliminating delays, you make sure your data's good, you're making sure you're fully utilizing that hardware, and everybody's happy. Your users are happy, your developers are happy, everybody's happy. I kind of hinted about how software RAID can burden your CPU. I'm going to do this at a high level. We can talk if you want to go into detail on it. We can actually get some pretty good metrics around this. But if your CPU is doing RAID, it's not doing your application. And we have seen high workloads, high intensive workloads around AI consume 30+% of a modern multi-core GPU just doing RAID. Seems like a pretty big waste of a resource if you ask me. Bottlenecks. You're using that CPU. Your CPU is still the traffic cop when it comes to moving data around between memory, between I/O, between drives, and back and forth. And if it's busy doing RAID calculations, you may have to wait for it to go and issue a command to go and get more data, go fetch it, and feed it to your application. And of course, when it is under load, obviously performance is going to suffer. That's pretty obvious. If you look at the AI data pipeline, I'm breaking it into 3 workloads. If you go look at AI workloads, you're either going to get 2 workloads, 5 workloads, 7 workloads, 9 workloads, but they really come down to 3 basic categories with a lot of grayness in between them. Data preparation is the first step. You're taking a bit of data and you're crunching it, you're munching it, you're making sure that it's good data, it's formatted properly where you can start to do training on it. What do you need? High throughput, IOPS, moderate, latency. Not really too much of a factor at this stage. Cost versus performance. You kind of want to balance it here. You don't want too lower performance, but you really want to start thinking about cost at the same time. Training. Now things start to get really interesting. Now throughput is very high. The faster you can get data into this, the faster you can do your training modeling. I was actually talking to a friend of mine at NVIDIA, and he said it is pretty common for the GPUs to be waiting so much in data that they can be 20-25% underutilized, just waiting for that data ingress. And a lot of that's because of the obvious bottlenecks, either getting data off the drives or Ethernet. Latency low, cost versus performance. Money is really no object when it comes to this, at least not at this stage. That'll probably change as it matures, but right now, performance. They're throwing money at it to solve the problem. Inference. This is the user interface. This is what we all use when we use one of the ask the questions to get the data results back. Throughput, not quite as critical. You still want good throughput, but it's not as critical as some of the other stages. IOPS, very high. You want to get that data through as quickly as possible. And the chunks can be both small and large, depending on your data set and what you use. Your latency, oh my God, make it as low as possible. Get the hops out of the system. And of course, cost versus performance, we're back into a balance point now. You got to fit that right thing for your right model. And that, and all these, by the way, is your mileage shall vary. If you get a Prius and you're trying to pull a trailer, you're not going to get 50 miles per gallon. You're going to get 20. You got a car like I got, yeah, we're just happy to pass a gas station. I like my cars. Bottlenecks, again, we're trying to eliminate them. We have them in the way. You're underutilizing hardware. You've kind of heard me say this a few times now. Insufficient IOPS means maybe you can't load the server up with enough users. So you have to deploy more servers to satisfy that user node. Well, how much money is a server with GPUs in it? It's approaching some houses in parts of the country. Not here. High latency. You want as low latency as possible with almost all these workloads. And of course, every single one of these AI workloads is SSD dependent. They really need SSDs. You're not going to see too much spinning media except for warm and cold backups when it comes to data preparation or offloading old engines. And again, I've kind of hinted to this. Performance is typically more critical than cost, but I do expect that to change over the next half a decade to a decade. It happens to every industry. But it's not all about performance. It's also about making sure your data is protected, integral, reliable, available. So data preparation stage, if you lose your inference pipeline, or if you lose a model, you're going to do a restoration at the very least. At least go back to a checkpoint. Process clean data. You've got an output. You've done all this work. Probably could be days in some cases. If you have to recreate that, wow, that's a lot of productivity lost and a lot of power down the drain. Metadata and label loss. Again, these are very commonly human generated today. Now you've got a team of people that have to redo their work. Now they're not happy too. Training, very similar story here. Got to restore if you have data loss. Train model means you have to probably restart. And inference, of course, this is less data critical when it comes to a loss, but it definitely affects your user experience. What happens? They get a delay, you have to repeat it back in, or it gets lost. Somebody's not happy, they're not getting results back in less than 5 seconds. And this is kind of where we come into the picture. We enable the performance. We also make sure your data is reliable and integral. Enable performance is like we hinted at, we're basically out of the way. We're getting that parity done on the GPU. We're leveraging what it does best. We're making sure we can push that data over the PCI lanes and not over purpose-built cables through a by16 card, or having to channel it and bottleneck it through your CPU. Kind of got the second one there. Yeah, and we're offloading the CPU for all that calculations for making sure that it can do more interesting things. Even on a GPU server, there's typically the CPU's doing something. It could be just management, but usually it's managing itself as part of the cluster and figuring out what's going on, and a lot of other people squeeze in other applications as well. Everybody does things a little different. Performance, and I know these numbers are a little small, sorry about that. We're getting near SSD line speed, so about 95% of what an SSD can do on read. Write is pretty similar. Write, we have a little bit more delay just because it's more write intensive. You have to do the parity calculation, etc. But still, much better than the rest of our competition. But like I said, performance is great. Who cares how fast it is? You have a question? Oh yes, good question. AE is AI Edition. So this is basically meant to run on a GPU. Rather than have a purpose-built card, we actually use a sliver of the processing power of one of these big Hopper or Blackwell GPUs, and use it as a background, infinitize it to a low priority task, so if necessary, you have something big come up, we can actually back away, get out of the way, and let your CUDA code run. Yes, sir? I'm sorry? I would say 90% of the computations are GPU. We still do some on the CPU, but most of what the CPU is doing is I/O fetches, DMA requests, that sort of thing. We try to offload as much of it as we can, and as the NVIDIA tool set gets more and more advanced, we see some opportunities to take it even further. Yes, sir. Night and day. So let's take one of the, I'm going to use the word competitor. I'm not going to throw a name out. Yeah, so he's wanting to know how our solution compares to like a traditional Broadcom RAID solution. So two things about the Broadcom. There's more than two, but I'll keep it down to two. First of all, that Broadcom is connected to a by16 PCIe. So you think about that. What's an SSD need? It's by 4. What's 4 divided by 16? How many drives can you support? 4. Any more than 4, you're sharing that bandwidth across how many extra drives you put on there. The second is their system on a chip, SoC, simply just can't process the IOPS and the throughput that you can when leveraging a GPU. GPUs are meant to push data around. So we're optimizing to it. Answer the question? Thank you. But yeah, going back to data resilience, we actually try to detect and correct errors before anybody can see it. So if you come across, obviously routine drive failure is easy. We're monitoring the smart like everybody else does. You see a drive fail or it looks like it's pending failure. We react accordingly, flag that drive as bad, throw an error up, make sure an administrator can go and change care of that drive when necessary. Obviously, we support RAID 6, which you have double fault protection. You can also do hot sparing as well. But mitigation of read errors, this can be done in the background and you never even see it. You're like, oh, well, that's not good. This did not pass the checksum. Well, because it's RAID, because it's striped, because the data exists in multiple places, we can go back and use a background process to recreate that data seamlessly. It is logged, so you can see if that does happen. So if you start to see a whole bunch of it, you can start to take action. But for the most part, the people using your application don't notice. Bad block recovery, same thing. We detect a bad block, we go and we flag it as bad. If we can recreate it, we will. More than likely, what ends up happening is that bad block ends up being bad forever, and we recreate that data somewhere else on the drive. And data integrity. By using hashes, we can make sure that that's from start to finish. The data looks exactly like it's supposed to. It hasn't been tampered with somewhere along the line. We actually have seen this proven in some of the lab environments where they try to inject errors, and we can catch those now. Health monitoring drives already went there. Fast rebuild. This is something that's not talked about a whole lot. Hardware fails. SSDs are complicated. We think of them as a commodity, but if you look underneath the surface, they're basically a computer. They have memory, they have storage device, they have a CPU on it, and a whole bunch of logic going on. These things will fail and do fail. What happens when they do? What happens when you have a bad day or you have a power event in there that actually knocks out a full system and you have to do a restore? Well, traditional RAID, doing a restoration, it can be days. It can literally be days. We did, this gentleman, Gil, just did an analysis just the other week with how many drives? 16, right?
Yeah,
15 drives.
but we found that reconstruction can be as high as, well, compared to MD rate, here we're able to cut down the reconstruction to about a third of the time. It would take similar software solutions by rate and similar results from Broadcom controller. And that's just in the reconstruction, right? You know, that's only one aspect of it. Your performance will also be increased by by a factor of 10, almost an order of magnitude, compared to the traditional solution. As Jason puts it, essentially when you're using a traditional solution, either you're spending CPU and memory resources, or you're funneling everything through a single card. Neither one is ideal. So our solution, which is actually out of band, allows you to, because we create the data map of, we know exactly where data is stored, we know where CRC data is stored, we know where parity is stored. We can basically pass selected segments to the GPU while the bulk of your data travels through the normal PCIe extender data. That's how we're able to achieve that. We like, and like Jason said, typically you will see anywhere from 95 to 98 drive speed for both reads and writes when using it. So you're getting the most out of NVMe that you're normally leaving on the table by using traditional.
Thank you, Gil. Appreciate that. So yeah, so you see how we got the complete package here. We're able to deliver high performance. We're able to keep your data as reliable as possible. Yes, sir. Yes, sir. Yeah, no problem. So what does this look like? I thought I'd do a case study so you actually see what an actual solution looks like in real life. This is actually University of Southampton. They're doing analysis on hospital imaging. And by doing so, we were able to speed things up considerably. High performance, low latency, as we talked about. And we're able to push, and this, I think this was 8 drives, if I remember right. We're able to push 20 gigabytes a second through the AI analysis to really night and day compared to what it would be for traditional RAID or a software RAID. 4 times faster than just a software RAID all by itself. And in summary, you need performance. We all want performance. It sells. It keeps those GPUs, those very expensive GPUs, busy, happening, and all your users happy. But let's be real. Data sizes are going through the roof. IOPS demands are going through the roof as well. Latency, everybody wants everything now faster, 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 because latency means that you're having to, something else is having to stop and wait for you to get that data. Data lakes, larger and more complicated. And I don't think that's going to stop anytime soon. I'm seeing some tiering of data lakes in some environments already. But what it really means is, you look at that sea of data, every drop in that ocean is critical. Every drop of that ocean has meaning. So you want to make sure that every drop is protected and reliable and something you can depend on. And if you have to recreate it, that's time, money, and opportunity cost. And like I said, data errors are going to happen. It's just reality. Everything fails. But being able to recover faster, three times faster, and that's an understatement. Actually, he actually did 3.66% faster in his testing the other day. But that's a lot of time where you're not generating any revenue and just have a piece of expensive hardware just sitting there idle. And that's it. I'm done. Any other questions? Thank you for your time.